Hello there, and welcome back. In this video, we're going to continue our discussion of hypothesis testing for the population mean mu. Let's first go over a couple of the basics for confidence intervals that we discussed last time, so we have some basic starting points and concepts associated to what we're actually going to be talking about this time. So, quick review. Last time. So let's suppose that we draw a simple random sample S from a normally distributed population whose mean is mu and variance is sigma squared. So if x is a normally distributed random variable, which we're assuming it is, then the z-score for that x variable will follow a standard normal distribution. So this is one of the principles that we discussed last time. So zx bar is going to be associated to a standard normal, and sometimes again people say a z probability density function. So let's look at a particular picture that we discussed in thorough last time. So here's our standard normal distribution, let's assume. That means this middle number is going to be equal to 0. And there was these two numbers above and below this value, and let's assume that this area is symmetric, where this number, this boundary, is known as the z critical value. And if this area is symmetric, that means this is going to be the negative z critical value. And this area in the middle we refer to as C, or the level of confidence. Let's assume that we're actually testing the null hypothesis that the mu is equal to some number called mu0, and let's assume that we're going to be working with a two-sided alternative where mu is not equal to that particular value. So if these are the things that we're testing against, what we usually do with this particular sample that we've drawn is we calculate, for example, the sample mean, because the sample mean is an approximation or a point estimate for the population mean mu, and then we can generate a margin of error for that point estimate, and that creates what we call the confidence interval. So remember what the confidence interval looked like. The confidence interval under some level of confidence C, so that's the same C here, for the population mean mu is always going to be equal to x bar minus epsilon and x bar plus epsilon, where epsilon is the margin of error for this particular confidence interval. And of course, we explored a few variations for the margin of error, but the simplest one of them all, assuming that this is indeed a z distribution, is going to be equal to that z critical value times the standard error associated to the estimate x bar for approximating the population mean mu. So this is of course the most basic one that we discussed, or the most fundamental one, I guess you could say, where this can also be rewritten as z critical value times the standard error of the estimate for x bar, remember, is sigma x over the square root of n. So if we know the standard deviation, then we can use a z distribution, so they'll usually come in pairs. Or another margin of error that we usually use is a t critical value in the scenario where we do not know the population standard deviation, and we replace that with the sample standard deviation for the sample that we have obtained. So these are the two most common margin of errors. Of course, if you know the population size or any other information, the margin of error would of course be fine-tuned. But those are just some of the basic things for confidence intervals that we discussed last time. So what are a couple of the pros for confidence intervals? So firstly, they are easy to understand and interpret. So if somebody says that, let's assume that the confidence interval is, let's say, 14 to 20. So if this is our confidence interval, that means our point estimate was equal to, let's see, the average or the middle of this interval. So that's going to be 20 plus 14 divided by 2. So that's going to be 34 over 2, which is 17. And let's assume that our claim was that the mean is actually equal to 20. So actually, let's not do 20, let's do 200. So if we got a claim that's equal to 200, clearly this interval and this point estimate are far from that. So we're going to be rejecting the null hypothesis because our evidence says that it's definitely not equal to 200. In particular, it's significantly less than 200. So that's pretty much how you would do about confidence intervals. So even people who don't know statistics sort of can follow the logic in the conversation for confidence intervals. But a downside is that there's actually more faster ways to conduct hypothesis testing. So there are faster ways to conduct hypothesis tests. Now, of course, you may lose a bit of understanding from the general audience, but if you're just doing it for a research purpose, or you're presenting to let's say, a statistical audience, these might be more appropriate, I guess you could say. So the second approach, aside from confidence intervals that we will discuss, is test statistics. Test statistics. In particular, test statistics for the population mean mu. So let's sort of build what a test statistic is and why it's actually equivalent to confidence intervals. So recall that we want x bar minus mu 0, keep in mind mu 0 isn't the mean of the population, it's the claimed value for the population, to be as large, positive or negative, as possible. And that's assuming we're working with a two-sided alternative here. So if we want x bar minus mu 0 to be as large as possible, that means equivalently, we want the square root of n times x bar minus mu 0 all over sigma x, or the square root of n times x bar minus mu 0 all over s to be as large, positive or negative, as possible. So yes, conceptually this is good enough, but why would we even go about making that statement complicated? Yes, they are true if and only if, simultaneously, valid, but why would we want to make this complicated? Because we actually know distributions associated to these things, and we actually can compare these numbers to objects in order to determine whether this is significant evidence or significant not evidence. So what do we compare test statistics to in the general discussion of hypothesis testing? So remember, this is very, very similar to the z critical value, or distribution for which z critical values are associated to. So this what we call a z-test statistic, which I'm just going to abbreviate by ZSTAT, is equal to, again, the square root of n x bar minus mu 0 all over sigma x. So in order to calculate a test statistic for the z distribution, you need to know a sample. So that means you know the sample size and the sample mean. You have to know the claim that you're testing against, and you have to know the population standard deviation. If you don't know the population standard deviation, then you're going to be using a t-test statistic, which is going to be equal to the square root of n times x bar minus mu 0 all over s. So what do we compare these to? That's the bigger question. So what do we compare these to? So let's go back to our original picture, because we need to determine, do we reject or fail to reject the null hypothesis based upon these two numbers, right? We're not looking at an interval, which is two numbers. We're looking at just a single number, or maybe two numbers, maybe, who knows? So remember back in the confidence interval world, this was a common picture that we looked at, where this area here is equal to C. So what did we want? So we wanted the claim, at least in the confidence interval world, to be as large as possible or as negative as possible from 0. So in the standard normal world, notice that these cutoff points where the confidence interval would be in our domain is actually equivalent to the z critical value and negative z critical value in the standard domain. So these are actually what we're going to be comparing our test statistics to. So let's do a little region in order to determine how we reject and fail to reject the null hypothesis. Because from our confidence interval world, if we do like a sort of parallel to it, we're going to be failing to reject the null hypothesis if our claim is in between the boundaries of our confidence interval. Similarly, we're going to be rejecting if we're too far from the middle. So that means if our test statistic falls in any of these regions, then we would have those corresponding conclusions. So let's summarize that. So if the z test statistic is greater than the z critical value, the positive z critical value, or the test statistic is less than the negative z critical value, then we will reject the null hypothesis. If the test statistic is in between the negative and positive z critical values, so that means we're looking in this region here, then we will fail to reject the null hypothesis. And that's how you would do hypothesis testing with test statistics. So let's just look at a numerical example of how that would sort of play out if we pretty much had no information to start with. So let's suppose that we draw a sample from a normally distributed population with mean mu, standard deviation sigma, both unknown. And for our sample, we get the following statistics. So let's assume our sample size was 34. Let's assume we calculate our arithmetic mean to be 127.5. And let's assume that our sample standard deviation came out to 11.4. For our hypothesis test, let's assume that our null hypothesis was that mu is equal to 130 and that we were using a two-sided alternative where u does not equal to 130. And let's assume that the probability of committing a type 1 error, let's assume we chose that to be 2%, equivalently choosing a confidence level of 98%. So based upon this information, how would we go about testing the claim that mu is equal to 130 using test statistics? So let's just go through the solution of that and see how that would play out and see why this actually is a little bit more quicker than confidence intervals. So notice if we use a two-tailed test, then our picture that we're going to be looking at is going to be something similar to this, right? So we want this area C to be equal to 98%. Now, which distribution is this? Is this a Z distribution or a T distribution? Keep in mind that we do not know sigma, therefore we have to use the standard deviation of the sample to approximate it. Therefore, the t-scores is going to be associated to a T distribution because we're sampling from a normal distribution. So that means this is going to be a t-critical value, and that is going to be its mirrored t-critical value with, of course, 0 in the middle. So since we have a two-tailed test with C is equal to 98%, that means this t-critical value is going to be associated to the 1 plus 0.98 over 2th percentile of the t distribution. And keep in mind we have infinitely many t distributions because we have to have a degrees of freedom. Since the degrees of freedom for a single sample test is going to be n minus 1, this is going to be equal to 34 minus 1, which is going to be 33. So we need to find the 1 plus 0.98 divided by 2th percentile of a t distribution with 33 degrees of freedom. And once you actually go through that process, you can find that the t critical value is going to be approximately 2.4448. Once we have a t-critical value, now we have something to compare our test statistic to. So let's calculate our test statistic and see what that comes out to. So the test statistic, or our t-test statistic, is going to be equal to, again, the square root of n times the sample mean that we obtain minus the claimed value of the population mean divided by the standard deviation of our sample. So that's going to be equal to the square root of 34 times the obtained sample mean, 127.5, minus the claimed value of the population mean divided by our sample standard deviation. So these numbers are just coming from the premises that I laid out in the very beginning. So once you actually go through these calculations, you're going to have that's approximately equal to negative 1.2787. So this is our test statistic. So now how do we conclude the hypothesis test via this approach? So let's look at our decision region. So these numbers here, so keep in mind this is going to be equal to 0, and this is going to be our t critical value. So our t critical value again is 2.44 approximately, so negative 2.44 is over here. So we're going to be failing to reject the null hypothesis if we're in this region, and we're going to be rejecting the null hypothesis if we're in this region. And this again is only true for two-sided alternatives. Our test statistic is negative 1.2787, so that's located right here. So since we're in between our positive and negative critical values, that means we will fail to reject. We will fail to reject the null hypothesis. So that's how we actually go about doing hypothesis testing with test statistics by comparing test statistics to critical values. So up to this point, we've discussed two methods of conducting hypothesis tests: confidence intervals and test statistics. One may of course ask, well, if we already have two methods, why create a third? So the first method, confidence intervals, are very easy to understand for the general audience. But in terms of computations, they do take a while to calculate because we have to calculate a bunch of little things. The standard error, the margin of error, the boundaries, and then conclude. For test statistics, we technically do not have an easy way of explaining them to the general non-statistical audience, so it does have that downside. But in order to calculate a test statistic, it's very easy to calculate. But you need two numbers in order to compare it to, the negative and the positive critical values. But for p-values, again, it's not very easy to understand to the general non-statistical audience, but what is the pro of p-values over test statistics? You actually only need one number for calculating p-values, in particular what we call the p-value. Now, a little downside here, in order to calculate p-values, you must first calculate test statistics, so therefore you cannot get totally away from test statistics because they actually are used to calculate p-values. So what is a p-value? So a p-value for a hypothesis test is the probability. So the p in probability is the p in p-value. So the p-value for a hypothesis test is the probability of obtaining your required test statistic. So that's why we need to know test statistics, because we need to first calculate it. But we know that the probability of obtaining a continuous number is virtually zero. So therefore we append something better, the probability of obtaining this test statistic, or something more in favor of the alternative hypothesis. So let's look at a picture to sort of see what this p-value actually looks like in the geometric domain and have some ideas on how we're going to go about calculating it. So let's look at for example, our z or our t distribution. So of course, this is going to be equal to 0. Let's assume that this is the z distribution just to make things a little bit more easier. So generally speaking, if we look at the t in our test statistic spectrum, then we're going to be comparing our critical values to our z critical values. So let's assume that we want to reject the null hypothesis. So if we're going to reject the null hypothesis, we're either going to have a test statistic in the upper tail. So let's assume our test statistic is there, and our negative test statistic is going to be there. So if they're mirror images, then they are equally strong with respect to each other. So what is the probability of obtaining z stat or negative z stat? Well, it's just going to be the area of this line, but lines don't have areas. So what is something more in favor of the alternative? So when we say more in favor of the alternative, we want to reject the null hypothesis with more and stronger evidence. So that means we want it as large as possible. So that means this area here in light blue is going to represent the p-value. So the p-value is shaded in blue. So that's the probability of getting our test statistic or something more in favor of. So for a two-tailed test, how are we going to calculate the p-value? So the p-value, some people will write it just as p or p-val or p-value, is just going to be equal to the integral from minus infinity to the negative z statistic world. And let's assume that's our normal distribution, plus the integral from the z statistic to positive infinity of our z distribution. Now, if this is a two-tailed symmetric test, that means these integrals are indeed equal to each other. So technically, you could say that the p-value is going to be equal to 2 times the integral from minus infinity to minus z stat of our z distribution, or 2 times the integral from our positive test statistic to infinity of our z distribution. You will get the same exact answer. It doesn't really matter which one you use because they are equal. So if you don't like negative numbers, then you'll probably want to use the integral from z test statistic to infinity. And that would be your p-value. So now that we have the definition of a p-value in front of us, now what are we going to compare our p-value to in order to determine whether we should reject or fail to reject the null hypothesis? So let's go back up to the picture that we previously discussed, and let's assume that this picture is actually accurate from the test statistic that we actually obtained. So notice that the area for which this teal region is in is actually located in the complement of our region of confidence. So remember that the complement of the region of confidence is actually equal to the probability of committing a type 1 error. So as long as the teal region is less than the green region, then we're going to be rejecting the null hypothesis. So that means we can simply compare the p-value to our alpha level in order to conduct our hypothesis test. So actually, let's go through an example of how we would actually go about doing this in our application world. So let's use the same exact example that we discussed before. So remember that our alpha value before was 0.02. That's coming from a 98% confidence interval. And also remember that our test statistic, t-stat, was equal to negative 1.2787. So if that is our case, then how are we going to be calculating our p-value? So negative 1.2787 and 1.2787 are located there. Since we're using a two-sided alternative, our p-value is going to have this particular picture. So that's our p-value. So how are we going to calculate it? So our p-value is going to be equal to 2 times the integral from 1.2787 to infinity of our t distribution, remember. So this is a t distribution with 33 degrees of freedom. Or you can do 2 times the integral from minus infinity to negative 1.2787. You're going to get the same exact answer of our t distribution. Regardless of which one you choose, you're going to get the same answer. That's going to come out to approximately 0.2099. So what are we going to compare this to? We're going to be comparing this to alpha. So how are we going to conclude that, and what's our decision process? So since the p-value is greater than alpha, where alpha is equal to 0.02, we're going to be failing to reject the null hypothesis. So generally speaking, the goal, if our goal is to reject the null hypothesis, is to have the p-value be as low as possible. So if you get a p-value that's equal to like 1 times 10 to the minus 50, that's actually a very, 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 very good probability value because it's practically close to 0, right? So the closer to 0 the possible if your goal is to reject the null hypothesis. So now let's actually take a moment and summarize all of the methods for hypothesis testing, and actually let's look at the conclusions that we get for confidence intervals, test statistics, and p-values and see if there's any difference between them. Let's suppose that we draw a simple random sample S from a normally distributed population, so that's one of the assumptions we're given here. Let's also assume that we actually do know the population standard deviation sigma, which is going to come out to 8.2. Let's assume once we actually gather our sample and analyze it, we have a sample size of 28, a sample mean of 83.4, and a sample standard deviation of 4.7. The null hypothesis for this particular claim was 75, so the claim is that the mean value mu is equal to 75, and let's assume that we're choosing a two-sided alternative that mu is not equal to 75. So as long as we get a point estimate that's significantly higher or significantly lower than 75, then we're going to be having evidence to reject this claim. Let's assume that we want a probability of committing a type 1 error to be equal to 4%, which is equivalent to saying that our level of confidence is 96%. So let's go through each of the methods and see what we're going to get for our conclusions. So let's start off with the first one that we learned, in particular confidence intervals. So method 1 would be confidence intervals. So how are we going to do confidence intervals? So first we need to figure out which distribution we're hanging out in, right? Because we're definitely working with a two-sided alternative, so our picture is going to be like this. We just need to figure out which distribution we're actually looking at here. So this is our area. We want this area, C, to be equal to 96%. So is this a Z or a T distribution? So since sigma is given and we're sampling from a normal distributed population, that means this is going to be a Z distribution. So one can find these counterpoints where this middle number is equal to 0, the Z critical value. One can find that the Z critical value is going to be approximately equal to 2.0537. Keep in mind this is not just used for confidence intervals, but also test statistics and p-values as well. So this number is going to be used for all three. For confidence intervals, what is the next thing we need? So we need to calculate the standard error of the estimate associated to using x bar as an approximation for mu. So since we know sigma, that's going to be sigma divided by the square root of n, and we don't know anything else about the population, so that's that. So sigma was given to be 8.2, and our sample size was 28. Therefore, this is going to come out to approximately 1.5497. So that's the standard error of the estimate associated to using x bar as an approximation from mu. And the next thing that we need to calculate is the margin of error. So remember, the margin of error for a z distribution is going to be the z critical value times the standard error of our estimate. Once you multiply those two numbers together, you're going to have a margin of error of approximately 3.1826. Once you have your margin of error and you have your point estimate x bar, now we can construct our confidence interval for our population mean mu. So our confidence interval and our level of confidence was 96%, and this is for mu, is going to be equal to x bar minus epsilon and x bar plus epsilon, which you can find to come out to 80.22 and 86.58. So that is our confidence interval. So now we go back to our claim. So our claim was that mu is equal to 75. So is 75 in between these boundaries? The answer is no. So since the claim value, which is going to be equal to 75, is not an element of our confidence interval, therefore we reject the null hypothesis, because we have evidence to believe that with respect to our sample that this claim is wrong. Or we're 96% confident based on our sample that the true mean is actually between 80.22 and 86.58. Now that we have our conclusion for our confidence interval, technically we do not need to do the other two. But let's just see if we actually get the same exact conclusion. Maybe they contradict each other, we don't know. So method 2 is test statistics. Test statistics. So we're working with a z distribution, so we definitely need to be calculating a z test statistic. So our z test statistic is going to be equal to the square root of n times our point estimate minus the claimed value of the mean divided by sigma, which we do know. That's going to come out to the square root of 28 times 83.4 minus 75, all divided by 8.2. Once you actually work out those calculations, you're going to have that that's going to come out to 5.4206. So that is our test statistic. Now we need to compare these to our critical values, which we already calculated. Our critical value was not that. Where's our critical value? Oh, it's hanging out in green. So 2.0537. So 2.0537. 2.0537. So that's our cutoff values for our test statistic decision criteria. So our test statistic is hanging out up there. So that's our test statistic. Z test statistic. So since our z's test statistic, since the absolute value of our z test statistic is greater than the positive z critical value, then again we're going to be rejecting the null hypothesis. Is this the same conclusion as before? Yes. So that's a good thing. So what about for p-values? Will we also get the same conclusion if we do about this from the p-value perspective? Take a guess. So p-values. So the p-value is going to be equal to 2 times the integral of our test statistic, which was, what was it? 5.4206. 5.4206, that's the positive one, so we're going to be integrating to infinity. This is a z distribution, so that's going to be our standard normal distribution. And that's going to come out to approximately 5.9 times 10 to the minus 8, right? So that's a very, very small number. So what do we compare it to? So since our p-value, this really small number, is less than alpha, remember alpha was 0.04 and that number is definitely less than it, then we're going to be rejecting the null hypothesis. So did we get the same exact conclusion in all three? Yes. But did we get the same conclusion in all three by chance? The answer is no. So that leaves us with this last statement that I'm going to leave you with, and that is this. So regardless of the approach you use, you will always get the same conclusion. So which method of hypothesis testing should you choose? It depends who you're communicating with, right? I mean, that's practically the only difference between them is, how they communicate, what you compare them to, the speed of the calculations, and so on. But those are the three most commonly used hypothesis testing strategies: confidence intervals, test statistics, and p-values for the population mean mu. Now, is there test statistics, p-values, and confidence intervals for the other parameters, for example, the variance and proportions? The answer is yes. So we're going to take a look at them in the upcoming videos, and I hope to see you there. Take care.